A dielectric is an insulating material which lowers the magnitude of the electric field in the space it fills. A dielectric is essentially an insulator whose charges are bound as insulators do. In the presence of an electric field, the molecules in the dielectric will have their positive and negative charges separated slightly, causing the molecules to be polarized in the presence of the electric field. Because of polarization, the dielectric in an electric field will give rise to thin layers of bound charges on the surfaces, creating positive and negative surface charge densities. These positive and negative surface charge densities will in turn produce their own electric field opposite to the direction of the original electric field that induced the polarization in the dielectric. Now, most capacitors have dielectric material between their plates. Suppose that it's a capacitor that's produced this uniform electric field that the dielectric finds itself in. So the left plate of the capacitor has the positive charge, and the right plate of the capacitor has the negative charge. So this capacitor having the uniform electric field is what produces the polarization of the dielectric material. The electric field between the capacitor plates is reduced by the presence of the dielectric because the induced surface charges in the dielectric cause an electric field in the opposite direction of the original electric field that charged the capacitor and induced the polarization in the dielectric. These fields tend to cancel each other, resulting in a reduction of the original field. Because a dielectric is an insulator, it inhibits the loss of charge through sparking between the plates of the capacitor, while at the same time increasing the capacitance of the capacitor in comparison to a capacitor without a dielectric. This increase in capacitance makes it easier for charges to accumulate on the plates, allowing capacitors to store more charge. The measure of the ability of a dielectric to reduce the electric field in the region of space it fills is given by the dielectric constant Kappa. Kappa is defined as the ratio of the magnitude of the electric field in vacuum to the magnitude of the electric field inside the dielectric material. Now, the electric field in a vacuum always possesses a greater magnitude than the electric field in a dielectric. Therefore, Kappa is always greater than 1 in a dielectric. Up until now, we've been doing all of our calculations by assuming that the electric field and the charges were placed in a vacuum, free of matter. In the presence of matter, an electric field is altered. And remember, the measure of the ability of an electric field to influence the space around it is called the permittivity of free space. So if the electric field is in the presence of matter, we have to account for it. We have to be able to measure it. And so we can't use the permittivity of free space anymore in the presence of matter. Instead, we have to include the dielectric constant. So we do have the permittivity constant, and the permittivity constant is directly proportional to the permittivity of free space. And that proportionality constant is the dielectric constant. So we will define epsilon to be equal to the product of the dielectric constant and the permittivity of free space. To date, all electrostatic equations containing the permittivity of free space must be modified by replacing that permittivity of free space with the permittivity equal to kappa times epsilon naught in any region that's completely filled by a dielectric material of dielectric constant kappa. This means that the electric field for a point charge in the presence of a dielectric is equal to 1 over 4 pi epsilon times the charge over the distance between the charge and the point in space squared. Gauss's law, which describes the electric flux through a closed surface, is written as the surface integral of the electric field is equal to the charge over epsilon. And the capacitance of a parallel plate capacitor is equal to the permittivity constant times the area of the capacitor divided by the distance. Each one of these formulas must use the permittivity constant that includes the dielectric constant. As long as we make that replacement, we can use everything that we've learned before.